Okay everyone, so today we are gonna look at solving boundary value problems. Okay, still in the boundary value problems topic. So we have this 2-point boundary value problem given as this. Okay, now last week lecture, if you still remember, I show you how you can solve this boundary value problem for the given boundary condition ya equals to alpha and yb equals to beta using finite difference approximation. Okay, you can use finite difference approximation. Now, the other way to solve this boundary value problem is using linear shooting method. Okay, this is what we're gonna learn in today's lesson. Okay, what is shooting method? Shooting method is done by assuming initial values that have been given if the ordinary differential equation were an initial value problem, but we have a boundary value problem. So how does it work? Okay, the idea of shooting method is to reduce the given boundary value problem. Okay, reduce the given boundary value problem to a system of first order ODE. Okay, so you don't have to use finite difference approximation. What you do, if you're given a boundary value problem, we can reduce it to a system of first order, and then you use linear shooting method. So what happens when you reduce? You will have an initial. You need two initial condition. Okay, you need two initial condition, but you will have one condition where you need to find until it reached the boundary value. Okay, it's maybe you don't see the idea right now, so let me show you how the steps work. Okay, so let's say we have given this condition here. Okay, where the initial condition given are ya equals to alpha, and then we have another condition. Okay, so maybe I'll just write it down. Okay, this is your given boundary value problem. Okay, to use the shooting method, first I'm going to consider the same problem. Okay, the same problem where it's continuous, x is continuous from a to b, but with initial values. Okay, initial values such as ya equals to alpha and y prime a equals to 0. Okay, and then I will get the solution. Okay, so the solution is y1x, let's say. And then for the second part here, so I will consider this problem again. Where x now same from a to b. Now the initial value that I'm going to consider is ya equals to 0 and y prime a equals to 1. We notice that the equation does not have the fx term. Okay, so the solution to this, we write it as y2x. Now once we obtain y1 and y2, okay, we can approximate this solution by using Runge-Kutta method. Okay, so we reduce the second order to a first order system, and then we can find yx by using a linear polynomial, let's say, given as y1x plus beta minus y1b over y2b multiplied with y2x. Okay, how do you obtain y1 and y2? Using any Runge-Kutta method. Okay, you can use order 2 Runge-Kutta method or Euler method. Okay, but they have to be the same method. Okay, so let's say y1, I use Euler method for this initial values here, and then y2, I also use Euler method for this given initial condition. Now to find yx, I will use some sort of linear polynomial technique. Okay, so once you obtain yx, I will estimate whether, because you have to use a starting initial condition, a starting condition. Okay, so once you get that, then you have to approximate. Okay, once you approximate, then you determine whether the solution has reached the desired boundary value. Okay, maybe I can explain this through example. Okay, let's look at this example. Okay, so the example say, solve the boundary value problem. That's it. Okay, solve the boundary value problem, where given as t double prime equals to 0.01 t minus 0.2. Okay, so we have the boundary condition when a is 0, my solution is 40, and then when b is 10, not my solution, the value is 40, and when t is 10, it is 200. So I know the interval is given from 0 to 10. Okay, so how can I solve this boundary value problem using shooting method? Okay, I'm gonna solve using shooting method. Okay, so what is the first step? The first step is to reduce the problem into a system of first ODE. Okay, so you have learned in numerical ODE how to reduce second order to a system of first order. So I will let t prime equals to z. Okay, so what is z prime? Z prime will be t double prime, which is 0.01 t minus 0.2. Okay, this is my t double prime. Okay, now you will see what I'm talking about. Okay, now you'll see what I'm talking about. So what is t0? Okay, t0 is given 40, no problem. But what is z0? What is z0? Z0 is not given. Okay, the initial value for z0 is not given. That's why you need shooting method. Okay, we cannot start with some value here, and then we're going to shoot out and see whether it reached the approximation until it reached the desired boundary for the value x equals to 10, and then we stop the iteration. Okay, so we need to assume now. Okay, so we will let's start with we need to choose the initial z0, any value. Okay, any value. Okay, so let's start with Z0. Z0 equals to 15. Okay, so we're going to start with Z0, 15, and we're going to use Euler method because it's very easy. Okay, what is Euler method? Okay, so Euler method, where you're always familiar with this term, right? Yn equals to y naught plus hf x naught y naught. This is Euler method. Okay, but now my equation involving t. Okay, so I'm gonna write it as Tn equals to t naught plus h f of x naught t naught. Okay, this is how I relate to the equation given. Okay, what is h? Did the question give anything about the step size h? Okay, I didn't mention the step size h, so we don't want to take this too long. So let's start with, okay, let's use h equals to maybe 2. Okay, and why did I choose 2? Okay, so let's see, why do I choose 2? Because I want to use 5 steps. So I start from x naught equals to 0, and then this is x5 equals to 10. Remember, the x is given for 0 to 10, right? So I need how many steps? x1, x2, x3, x4, and x5. Okay, so I have 2, 4, 6, 8, 10. Okay, so I need to use 5 steps, 5 iteration. Okay, so let's start with n equals to 1. Okay, let's start with n equals to 1, the first iteration. So I have t1 equals to t naught plus h f of x naught t naught. Okay, what is t naught? Okay, look at this thing again. Okay, so if I for this condition, okay, my t initial consists of t and z. So 40 and 15. Right? So t1 equals to, initial is 40, 15 plus 2. Okay, this is the f. What is the f? This is the f, the problem. Okay, so start with z, which is 15. Start with 15, and then 0.01 t naught, 40, t naught is 40, minus 0.2. Okay, now again, okay, you need to calculate this using calculate. Is very quick. You can do this. Okay, I've already done this earlier on, so I'm just going to write the answer. Okay, so this will be 70 and 15.4. Okay, so what is x1? x1 will be x naught plus h, which is 0 plus 2, which is 2. Okay, we are not there yet. We need to find until x5, which is 10. Okay, continue. For n equals to 2, I have t2 equals to t1 plus h f of x1 t1. Okay, so what do I have? t1 70, 15.4. 70, 15.4 plus 2. Now, the problem here. So, I have Z. Okay, what is my Z? This is so let me just write it down. If you still don't know, my T consists of, the big T consists of this one. This is my T0, T1. This is my Z1. Okay, so if I'm talking about this problem here, the first equation is for Z, right? So T prime equals to Z. So my Z is 15.4. And then I have 0.01 T1 minus 0.2. Okay, so use your calculator. You should get 100.8. Okay, 70 plus 2 times 15.4, 108. 15.4 plus 2 times this whole term here should give 16.4. Okay, so what is my x2? x2 will be x1 plus h, which is 2 plus 2 equals to 4. Okay, we have obtained n equals to 2. Okay, again, this is my T, this is my Z. Okay, n equals to 3. I have T3 equals to, okay, T2. Okay, so I don't know what happened. I think I'm still recording here. Okay, that's good. I'm still recording. So what is T3? What is T3? T3 is equals to T2 plus H f of x2 T2. Okay, so we have obtained T2, which is 100.8 and 16.4 plus 2. Okay, now the same thing again, where we have Z first, so 16.4 and then 0.01 T, which is 100.8 minus 0.2. Okay, so use your calculator. You should get 133.6 for the first value of T, and then the value of Z should be 18.016. Okay, so x3 is equals to x2 plus h, which is 4 plus 2 equals to 6. Okay, we need 2 more iteration. So keep going. So when n equals to 4, I have T4 equals to T3 plus h, f of x3 T3. Okay, so what is T3? So I have, this is my T, this is my Z. So I have 133.6, 18.016 plus 2, Z first, 18.016, 0.01 multiply with T, 133.6 minus 0.2. And you should get 169.632, 20.288. Okay, I am excited because we are now finding N5. Okay, so we have found X4, which is 6 plus 2 equals to 8. And we have N5. T5 equals to T4 plus H, f of X4 T4. Now you can see that I'm writing very fast. This is where I can make a careless mistake, right? So I need to slow down. So my T4 is 169.632. Okay, and then this one is 20.288. okay, plus 2, and the function z, which is 20.288, and then my other function will be 0.01 t, 169.632 minus 0.2. Okay, I have obtained 210.208 and 23.28064. Okay, what is this? The number is quite big, and okay, don't worry about it. We have not come to the conclusion. So what is x5? x5 is x4 plus 8, which is 8 plus 2, 10. Okay, so what we obtain here, we have obtained that in the question is given, if you remember, okay, or I can show you, I gotta go all the way up. Okay, the boundary condition that given earlier on for the question is T10 equals to 200. Okay, but we started with the initial guess. The initial guess that we started was, okay, we started the initial guess Z0 is 15. Okay, and what does T510 gives you? T510 gives you. Okay, let's look. What is T5? This is the one that we have obtained. Okay, so T5, oops, this is not T, so I'm just gonna undo it. Okay, so okay, let's write it again. Okay, so we have T510 is giving me this answer, right? 210.208, 23.2864. Okay, so we can see that this is, we know this is my T, this is my Z. Okay, the boundary condition given is T10 is 200. Now look at my prediction with Z0 equals to 15. What do I get? I get T510 is 210.208. It's bigger. It's slightly higher than the condition given. Okay, so what do you need? You need to adjust. I need to adjust the choice of my Z initial. And then I need to approximate again using Euler method. So I need to adjust. Adjust Z0. So I cannot use 15. 15 is giving me a bigger value. So let's try Z0 equals to 10. Okay, let's try Z0 equals to 10. Now I need to use Euler method again. With this choice. So my initial T naught is 40 and 10. Instead of 40 and 15 you started earlier on. Okay, so I hope you are still with me. So because we want to find the given initial condition for Z. Okay, that's why what we are doing now is to find the initial condition for Z. So let's try it again now with T naught 40 10. Okay, so do it again the Euler method. For I equals to 1, for n equals to 1, we have T1 equals to T naught plus H f of x naught T naught. Okay, so we have 4010 plus 2 and the function. Okay, z is 10. This is my z, this is my t. So 10, 0.01, 40 minus 0.2. So, use your calculator to check. You have 60 and 10.4. Okay, I'm not going to repeat this, but you know this is my t, this is my z. Okay, so x1 is 2. Now for n equals to 2, I have t2 equals to t1 plus hf of x1 t1. So I have 60 10.4 plus 2, 10.4 and then 0.01, 60 minus 0.2. So what do I get? 80.8, 11.2. There you go. Okay, and then obviously x2 will be 4. So n equals to 3, we have t3 equals to t2 plus hf of x2 t2. So I have 80.8 and 11.2 plus 2 of 11.2, my z, and then 0.01, 80.8 minus 0.2, which is equals to 103.2, 12.416. Okay, my x3 will be 6. 4 plus 2. Okay. Now for n equals to 4, I have t4 equals to t3 plus hf of x3 t3. So we have 103.2, 12.416 plus 2, 12.416, 0.01, 103.2 minus 0.2. Okay, now the same thing, finding this value here is give you 128.032 and 14.08. This is a very simple operation here, so you just have to use your calculator. Okay, so we have obtained x4 at 8. Now for n equals to 5, I have t5 equals to t4 plus hf of x4 t4. So I have 128.032, 14.08 plus 2, then the function 14.08, 0.01, 128.032 minus 0.2. Man, this is getting too long, right? Yeah, I know. But hang in there. We have 156.192, 16.24064. Okay, so I have find two values here. So what is x5? x5 equals to x4 plus h, which is 8 plus 2, 10. Okay, now remember in the beginning I said to use this shooting method, I need to approximate two values of y1 and then y2, right? So now I already obtained two value of y1. Okay, so what I have, for z0, when the initial is 15, I have t10 equals to 210.208. And then my second guess for z0 equals to 10, t10 I have obtained 156.192. Okay, the third guess I can approximate by using the linear interpolation. Okay, the linear interpolation. such as Z0, the initial can be obtained by T10 plus 15, okay, 15 minus T10 over T210 multiply with T20. Okay, I know the equation looks a bit weird compared to the standard one that I have given earlier on. Okay, the standard one should be like this. Okay, the standard one, let me just write it down here. So yx equals to y1x plus beta minus y1b over y2b y2x. Okay, this is the what I have done here. Okay, so what is T10? T10 is 10. 10 plus 15 minus 10 over, what is T210? T210, okay, this is at 10. Okay, I will say this one, 210. Okay, 210, but we have two values here, right? So we have 210,208 minus 156.192. Okay, multiply with T2. Given the given condition will be 200 minus 156.192. This is the linear interpolation that we wanna obtain. Okay, so 15 minus 10. Okay, 15 minus 10, and then this divide by this one minus this one, multiply with 200. 200 is the exact. This is the exact boundary condition that we want to obtain. Okay, the question is given for T40 equals to something. I mean, I forgot. 200 minus with your approximation for T10. Okay, recall this. This is kind of familiar. This formula is actually familiar. Okay, so what is this formula? I want you to find out the name for this formula. Okay, so what you get by doing this calculation, you will end up with Z0 equals to 14.055095. Or I can use my condition 14.06. This is the estimated initial. Now, how do you know whether this value is correct or not? How do you know? You need to solve the Euler method one more time. Okay, when you use one more time, and then you can see what's the value you obtain for T at 200. Do you want to try? You want to try? Okay, let's try. Let's try, okay, to prove to you that this will be the good choice. Okay, now let's use this one and use the Euler method again for 5 iteration. So my T naught now is 40 and 14.06, or maybe I use the whole thing. Okay, 055095. Now, why I want to use the whole thing? Because I want it to be very accurate. Okay, I want it to be very, very accurate. Okay, so for n equals to 1, we're continuing the same approach just now. T1 equals to T naught plus HF x naught T naught. So I have 4T, 14.055095 plus 2, we have 14.055095, 0.01, 40 minus 0.2. So you will get 68.1102. This one is 14.4551. Okay, I'm not going to write the x anymore. Okay, so continue with T2. For n equals to 2, I have T2 equals to T1 plus h f of x1, T1. Okay, x is not even, you're not using x here. You just need it to approximate the time. Okay, so T1 is 68.1102, 14.4551 plus 2 times the function, which is 14.4551 over 0.01 multiplied with 68.1102 minus 0.2. Okay, you get 97.0204, 15.4173. Okay, now for n equals to 3, I have T3 equals to, now I know you are feeling tired, okay, but just hang in there, T2 plus hf of x2 T2. Am I doing correct? Okay, if I do too fast, I can get lost. Okay, let's calm down. T2, okay, 970204, 15.4173 plus 2, 15.4173, 0.01 multiplied by 97.0204 minus 0.2. You have 127.8550, 16.6557. Okay, that is my T3. Now what is my T4? T4, I have T3 plus hf of x3 T3. So I have 127.8550, 16.6557 plus 2 times 16.6557, 0.01 T, 127.8550 minus 0.2. So what do I have? Okay, my hands are getting tired. Okay, so I have 161.7704. Now that is a good reason why I choose the step size h is 2, because we just do 2 iteration. Okay, can you imagine if you're doing more than 8 or 10 iteration? Okay, but obviously the more iteration you do, although it requires more computational time, but the solution should be quicker. Okay, I mean the approximation should be close to the required solution. So we have T5 is T4 plus hf of x4 T4. So I have 161.7704, 19.1148 plus 2, okay, 19.1148, 0.01, 161.7704 minus 0.2. There you go. I'm very excited to write it down. The last value will be 200. Okay, please check. I hope you get 200. 21.9502. So what do you obtain? What do you obtain? So with the choice of Z initial, Z0 equals to, what do I get? 14, right? I get 14.055095. The reason I'm not using it to 2 decimal places, so I want to make sure I get exactly 200. Okay, if you start with 14.06, I mean you'll have 199 or something. Okay, but it's close enough. So this gives exactly for T510, exactly. So this is because the ODE that we are solving is linear. So linear interpolation performed with the first 2 guesses are good enough to get T10 exactly. Okay, Okay, so what that mean? Okay, so now you're gonna look back at your boundary condition. Have I solved the boundary yet? No, you haven't solved the boundary yet, because all you are doing is using shooting method to determine the initial guess. Okay, so look back to this problem again, which is equals to 0.01 t minus 0.2. So now I can write t0 equals to 40 is given, and z0 equals to 14.055095. Okay, so you can now you have solved it actually. Okay, with the two initial problem here, I have obtained the value that I want for both t and both z value. Okay, so this is the idea of shooting method. You start with one condition that a condition that you don't know, and then you try to shoot as close to the given desired interval that you need. Okay, so this is the idea of shooting method. Now obviously I can use Scilab to prove this. Okay, perhaps Scilab can work better than the writing that we have to do. Okay, maybe I can show you how Scilab works for solving this shooting method. Okay, so open your Scilab. So you need to open Synode. Okay, so what I want to show you in Scilab is that we want to write that shooting method using Scilab. Okay, so we want to use shooting method to solve Scilab. Okay, so this is the problem that we want to solve. T double prime equals to 0.01 t minus 0.2 for given t0 equals to 40 and t10 equals to 200. Okay, this is a given boundary value condition. You want to use Euler method. We want to use Euler method. Okay, so there are few things we need to consider. Okay, few things we need to consider. The first thing is we need to define Euler method. Okay, so let's we need to define. So what you need to do, you need to define Euler method, and then you need to define the problem. Okay, define the problem, and then we're going to use the shooting method way. Okay, so open a new file and define the function. Okay, the problem. So we have function. Okay, write it as y new equals to, I'm going to write it as f new y. So what we have here, so instead of using t and z, okay, I can use as y1 and y2. Okay, y1 equals to y2. Okay, this means this is z. Okay, according to our hand calculation just now, and this is my t, 0.01 multiplied by y1 minus 0.2. Okay, I don't have so many bracket here. Is that correct? Okay, yeah. So this is my t. Okay, so let me just comment here. My y1 is my t prime. Okay, in the notes, and then my y2 is my is this how I write, right? Yeah, my y2 is my z. Yeah, this is how I've defined. I mean, let me just look at it again. So I have t and z. So the question in my book says t prime equals to z, right? And then I have z prime equals to 0.01 times t minus 0.2. Okay, this is what given. This is what the question is given. Okay, but so I'm referring my y1 as my t prime and y2 as my z prime. Okay, okay, good. And save it as f new. Save it as f new. Okay, f new. That's it. The next one is to define the Euler method. Open a new file. So this is how you define. Though you have done this before, I guess. So if you have the Euler method coding, so you can use the same coding, or you can write it down, but make sure you put it in a different folder, not in the same folder that you have. Okay. So what is y out equals to y naught plus h times f new y naught. Okay. Now for simplicity, this actually should be like this, the Euler method, right? Y naught plus h times f x naught y naught, right? I'm not going to consider x here. Okay, I don't want to consider x. Okay, so I'm just going to write it in terms of y here. Okay, save it now. So you have Euler. Oops, I think I saved it somewhere else. Where did I save it just now? Save as. I want to make sure I have it in the folder that I used just now. Where did I save it? Oh dear, this is very important to find out. Where did I save my f new? It's not in document. Okay, I just have to find it again. Okay, so look at, okay, I'm just gonna create a folder here just to be safe. Okay, so just to be safe, that folder is called in my in my document folder, it's gonna call shooting method. Okay, so I'm gonna save my Euler inside this shooting folder. Okay, so I have Euler saved, and then this function now, where did I save it? So okay, I need to save it again inside my shooting method folder in document, shooting method. Okay, save. Okay, press the execute button for f new, press the execute button for Euler. Okay, go back to my main file now. Okay, now I need to define all the given initial here. Okay, so I need to define all the conditions. Okay, what do I have? X naught equals to 0, y naught equals to 40. Okay, so this is the value given at t. Okay, I'll just write it in case you're getting confused. T0 equals to 40 as given in the note just now. And then we have our xn. Xn is 10. Okay, what is yn or y 200? So what is this? This is my t at 10. The boundary condition is given as 200. Okay, now I need to define the define the starting z initial. Okay, so what I start with, I'm going to write choice of z00. The first z00 initial I used was 15. Okay, so this is what I used. Starting z initial is 15. And then the second choice of z initial, I have used 10. if you recall. So Z0 equals to 10. And I have 5 iterations. Okay, so how do I compute the space? So first, to find the step size h, I have xn minus x naught divided by 5. So my h is 2. Okay, so my h is 2. Then I'm going to set the initial condition as a vector. If you look at here, my f new here is 2 dimension. Right? So one is z and one is t, right? So let's write it as y initial 1 consists of my y naught and z00. Okay, so I have this is what it means. T equals to, if you look at my first computation, start with 40, 15. This is my first Euler computation. Okay, so now I'm going to use Euler method to solve. So what I have I'm calling the function Euler. I equals to 1 to n and the function. Okay, I'm going to look at this Euler method here. Okay, Euler method here. Okay, so what do I have? I'm going to call it as y1 equals to Euler y1h. Now the reason I'm writing y1 and y1, I don't have, because I need to update my Euler with my y values. But if I do that, I don't have to update them. So what is y1? Y1 equals to my y in 1. Okay, that should give me the first approximation. So let's write it down. M print f. Okay, the approximation is percent 4 decimal places /n for y1. Okay, so this is what it give you my y1. Okay, so then what do I do? So I need to adjust. Okay, how do I adjust? Adjust the initial condition. My second Euler condition that I use. So I have y in 2. The second choice is y naught and then z0 1. Okay, this is my second initial. The first one is this one, and then the second one is z0 10. Okay, so do again the Euler method, the same thing. What do I did earlier on? I'm just going to copy and put it here, but I'm going to call this as y2 equals to y into this initial. Put it here, y2, and then I'm going to copy this m print f so that it can display the choice of y2. Okay, now I have two solution approximation, so I'm going to use linear polynomial. Okay, linear polynomial. So to find the z0 is equals to z01 plus z00 minus z01 divide by y1, the first y1 minus y2 for the first choice of my y, multiply with yn minus y2 1. Okay, so what I'm doing here, I'm just considering my solution that I obtain will be for the first value of t here. Okay, so what do I have? I'm going to copy this, same thing again, where I'm going to write the third estimate is z0 equals to percent f and z0. Okay, this one. This is my third choice of z. Okay, now to check this is the correct, so I have y in 3 equals to y naught, comma, z naught. Okay, so I'm doing it very fast. I'm assuming I'm going to have some error, but I will adjust it later on. Okay, so use the Euler method for the third time. So where my y3 equals to y3 in, this is y3, y3. So, and I'm going to copy this term here. I'm going to copy this term. So the approximation is for my y3. There you go. So, okay, let's just try. Okay, let's try. I might have very many error or none. I don't know. So let's try. Save it as shooting 1. Okay, and then execute the button. Let's see, what do I get? Okay, see, there's so many problem here. So define y new is undefined. So let's look at my f new function. Okay, obviously I don't have my y new here, so I need to define what is my y new. My y new consists of my y1, y2. Okay, I missed that part. Okay, that's it. So now I have y new. So save and press the execute button. Okay, press again the Euler button and then the shooting method. Okay, let's see what you get. Oh, there you go. Okay, the first approximation initial is 210, exactly like what we have obtained here. Okay, and then the second one is 156.192, and with the third estimate 14.0051 that I've shown here, okay, I get the approximation is 200. Now I bet Scilab is much easier than doing all this calculation. Okay, you have to agree with me. Okay, so but you need to write this hand calculation so that you know how to put it in Scilab. Okay, class, so that is about linear shooting method. Okay, so the idea is to reduce the boundary value problem to a system of ODE and then find the initial guess to obtain the solution. Okay, thank you for watching my video. Ask me question if you have anything. Bye for now.